In this video, we are going to introduce root locus. So, this technique is generally used to get the relative stability analysis or to find out the roots. So, here this root locus is having some construction rules. That means to construct any root locus, we need to follow some conditions. That conditions we are going to discuss here. The first condition is the root locus is always symmetrical about real axis. You know about imaginary axis and real axis. So, that is, you can see here, if you consider any S plane, here you are having j omega axis and here you are having real axis. So, always your root locus is symmetrical about your real axis. So, now coming to the second point, the root locus always starts from the open loop pole and terminates at finite open loop 0 or infinity. Generally, the root locus always starts from open loop pole and terminates or ends at finite open loop 0 or infinity. That means, here for example, if you are having poles like this, so here for example, you are having root locus like this, symmetrical about real axis. For example, if you are having any 0 here, your root locus may start from here, any open loop pole, and it may end at open loop 0 or it may terminate at infinity like this or like this. It may terminate at open loop 0 or it may terminate at infinity. So, here if you see, so it is going to terminate at infinity. We do not know the end of that, whatever the root locus we drawn, we do not know the end of that. So, in this case, so this may terminate at infinity or this may terminate at open loop 0. So, here the number of branches terminating on infinity, the number of branches terminating at infinity is equivalent to p minus z, where p is the number of poles and z is the number of zeros. So, this is number of poles and this is number of zeros. That means, for example, if you are given with any open loop transfer function like this, k by s into s plus 1. So, here how we can determine the number of zeros? So, by observing the denominator, we can determine the number of zeros. Here the number of zeros is equivalent to 0. Why? Because we are not having any s term. If you are having k into s plus 1, then s is equivalent to minus 1 is the 0 in the numerator. So, here we are not having anything. So, number of zeros is equivalent to 0. And here the number of poles is equivalent to s equivalent to 0 pole, s equivalent to minus 1 pole. So, totally you are having number of poles is equivalent to 2. So, the number of branches, so here the number of branches is equivalent to 2 minus 0 is equivalent to 2. So, here we are having one condition. Actually, whatever the branches that are going to terminate at open loop 0 or what are the branches terminating at infinity, for that we are having condition. That is, if poles are greater than zeros, then your branches are going to terminate at infinity. If zeros are greater than poles, then your branches are starting at infinity. So, you can observe the difference. If pole is greater than 0, that means, so if pole is greater than 0, then branch start at infinity. not start, branch terminates at infinity. So, whenever poles are greater than zeros, so branch will terminate at infinity. If zeros are greater than poles, then branch will start at infinity. Branch will start at infinity. So, this is the difference between the number of poles and zeros. How the branch is going to vary. If poles are greater than zeros, then branch is going to terminate at infinity. If zeros are greater than poles, then branches are going to start at infinity. Now, coming to very important fourth point, a point on the real axis lies on the root locus if the number of open loop poles plus number of open loop zeros on the left half of S plane must be odd. So, that means, for example, you are having your S plane like this, j omega axis, and this is real axis. You are having 3 poles at origin, 1 pole, and here is 1 pole and here is 1 pole. So, here to the left half of S plane, your number of poles plus zeros must be odd. For example, here from here to here you can observe only 1 pole. Observing only 1 pole is nothing but odd. From here to here, my root locus is symmetrical about real axis. So, here I am having root locus. Whenever this pole started, then my poles count is, total number of poles or zeros count is increased to 2. When you are hearing 2, so that is the even number. Always the open loop poles plus zeros must be odd to draw the root locus. So, I am just moving in this way. So, in this point, if anyone asked you how many poles are there in your path, so only 1 pole. So, after crossing this pole, how many poles are there means we are having 2 poles. So, here you are not going to consider the root locus in this position. After crossing this pole, so again you will get root locus. Why? Because the number of poles from here is 1 plus 1 plus 1, 3. So, totally 3 poles will be there. So, here this part won't come because the addition of open loop poles and zeros. So, in this position from origin is equivalent to 2. So, it must be odd, not an even value. But here in this position the number of poles plus zeros is equivalent to 2. That is why we are not considering that position. So, that is the meaning of this point. After that, the angle of asymptotes. So, whatever the branches we are taking, that branches angles are nothing but asymptote angles. So, here if P greater than Z, P greater than Z means, so your value is terminating at infinity. That means your branches are going to terminate at infinity. So, the asymptote angles are phi A is equivalent to 2q plus 1 into 180 divided by P minus Z, where q is equivalent to 0, 1, 2, so on, P minus Z minus 1. And if Z greater than P, the branches will start at infinity and the asymptote angles are phi A is equivalent to 2q plus 1 into 180 divided by Z minus P. So, where q is equivalent to 0, 1, 2, so on, Z minus P minus 1. So, this is very important conditions we need to follow when you are writing root locus. Some more conditions are there that we will discuss in the next slide. That means, so what is the centroid we need to consider and what is the angle of departure and angle of arrival, that we will see in the next slide in the same video. In previous 5 points, we discussed points about root locus, that means the construction rules for root locus, as So root locus is symmetrical about real axis, that means the first 5 points, in the first 5 points we discussed, the root locus is symmetrical about real axis, that means so it is symmetrical to real axis. And after that, so always root locus starts at open loop poles and terminates at open loop 0 or infinity. For example, if you are having poles like this, it may starts at open loop pole, any open loop pole, it may terminate at 0 or it may terminate at infinity like this. And another point we discussed that a point is said to be on root locus whenever the sum of open loop poles plus zeros must be odd. That means, so here if you are having 3 poles like this, so in this root locus path, so up to here there is only one pole from origin. From here onwards we can say we are having 2 poles. So that means when you are moving to this side, in the back section how many poles are there means we are having 2 poles, that is why we are not going to consider this section. And coming to here, from this pole onwards the number of poles will be 3 again, that means from the origin moving towards minus infinity region, the number of poles plus zeros must be odd to write the root locus or to draw the root locus. Here I am having root locus here, but I am not having here. Why? Because so at this point how many number of poles plus zeros are there in the way of that origin means we are having 2 poles. That is why I am not taking that condition, I am not taking that region. Why? Because my number of poles plus zeros must be in odd number. And coming to poles and zeros, so if poles are greater than zeros, then the branches will terminate at infinity. If zeros are greater than poles, branches will start at infinity. And one more important point is, for example, if branch is terminating at infinity, then we can say a 0 is there at infinity. If a branch is starting at infinity, that is the meaning a pole is there at infinity. So that is very important points. If you are saying your branches are terminating at infinity, terminating at infinity means, so that implies a 0 is there at infinity. If your branches starting at infinity, that means if zeros are greater than poles, then you are said to be your branches are starting from infinity. So we can say if branches are starting at infinity, we can say a pole is there at infinity. Why? Because so always your root locus branches starts from poles and terminates at zeros. So that is why we given that clarification. And now here coming to the centroid. Centroid is nothing but meeting point of your branches or asymptotes in the real axis. So here for example, if you are having root locus like this, if you are having so poles like this, so you are having asymptotes, 3 asymptotes. So that asymptotes will meet at centroid in the real axis. So this is the centroid. So to calculate that centroid, the formula is sum of real parts of poles minus sum of real parts of zeros divided by number of poles minus number of zeros. This is the formula to calculate the centroid for the root locus. And coming to breakaway and break-in points. So here I need to discuss one more point. So whenever you are having zeros, as I told you, always root locus starts from poles and ends at or terminates at zeros. So here this is going to terminate at 0. When 0 is there, an incoming arrow will be there. To get this incoming arrow, we need to have any break-in point. So that means like this or like this we need to have that break-in point. Or in case of poles, for example, if you are having poles like this, from this poles we need to draw away from poles, that means like this or like this. So we need to draw the arrow marks away from that poles. So here when you are writing that arrow marks away from that poles, so this line may go like this or like this. So that means, so by entering like this, the direction may be like this or like this. That means break away points. It's going away from poles. Here, coming to here, this is going to the zeros. That means the arrow marks going into the zeros. Here the arrow mark is going away from the poles. That's why whenever you are having two poles, definitely we are having breakaway points. Whenever you are having two zeros, in between two zeros, we may have break-in points. To calculate break-in points or breakaway points, so we need to have dk by ds is equivalent to 0 condition. By solving dk by ds is equivalent to 0 condition, so we are going to get breakaway or break-in point. So now the angle of departure and angle of arrival. So when we will get this angle of departure and angle of arrival means, whenever you are having imaginary roots, whenever you are having imaginary poles or zeros, then you are going to get the angle of departure and angle of arrival when you are having imaginary zero. So here the angle of departure from open loop pole is given by phi p is equivalent to plus or minus 180 degrees into 2q plus 1 plus 5, where q is equivalent to 0, 1, 2, 3 and so on. And here where phi is equivalent to theta 2 minus theta 1 plus theta 3 plus theta 4. Why I given this equation means, for this diagram I given this equation. Please observe clearly. For example, you are having an imaginary pole like this. So if you are having imaginary pole like this, a plus j, for example, if you are having like this. So here this is a and this is a. So if you are having like this is your imaginary root a. So now here this imaginary root, we need to calculate the angle of departure. Why? Because that is a pole. So angle of departure can be calculated like this. For example, if you are having a 0 like this, and if you are having any pole like this and like this, and another pole like this. So how you will calculate means, so you will take lines like this, and now here this can be calculated like this. So this is theta 2, this is theta 3, theta 4 and this is theta 2 and this is theta 1. You just consider like any angle. Theta 4, you just consider like this. You can see. Now how you will calculate this one means, so if you want to calculate angle of departure at A, you need to consider this equation. In general, we are going to consider 180 plus phi as angle of departure. You are going to consider q as 0 and 180 plus phi you are going to consider as angle of departure. To calculate this phi value, so here whatever the angle making by this 0 with this a, that you just consider here. For example, if you are having two zeros, how many angles created by that zeros, that you will consider here, minus angles created by poles on the real axis. So here phi is equivalent to angle created by zeros minus angles created by poles, sum of angles created by poles. Here as I am having only one 0 here, the angle created with 0 is theta 2 minus the sum of angles created with remaining poles is equivalent to theta 3, some theta 1 and here theta 4. I am going to consider like this. For example, if you are having like this, so here you are having only 2 poles and 1 0. So, this is the equation for that 3 poles, and so this is imaginary pole. Remaining 2 poles is here. So, now here for example, if you want to calculate the angle of arrival at open loop 0, then the same equation we are going to use, but minus 5 we are going to use. The equation 5 will be same. For example, if you are having more number of zeros, here we are going to add that angles made by that more number of zeros. That means, for example, theta 1, theta 2, theta 3 are the angles made by number of zeros, and theta 5, theta 6, theta 7 are the angles made by number of poles. So, we are adding that angles made by number of zeros and subtracting the number of poles. That means, the angles made by number of poles we are adding and subtracting from this one. So, like this we are going to calculate the angle of arrival at a point open loop pole and open loop 0. And here the intersection of root locus on the imaginary axis is also very important point. That means, here for example, if you are drawing any root locus, then for example, if your root locus is like this, then at which point you need to intersect this imaginary axis. That can be decided by the intersection of root locus branches with the imaginary axis. This can be decided by the Routh array. Again we are going to use Routh criterion. So, all these 10 points are very important. So, what you need to keep in mind when you are drawing your root locus diagram is, so root locus is always symmetrical about real axis, and you need to find out the number of poles and zeros according to the number of poles and zeros. By taking p minus z or z minus p, you are going to get the number of branches. After getting number of branches, you need to find out the angles made by that branches or asymptotes. So, by using asymptote angle equation, after that you need to find out the centroid, that means meeting point of that asymptotes on the real axis is nothing but centroid. After that you need to find out breakaway or break-in point by using dk by ds is equivalent to 0. So, always in between 2 poles you may have breakaway point, in between 2 zeros you may have break-in point. So, that can be calculated by using dk by ds is equivalent to 0. The angle of departure when imaginary pole is there, we will get angle of departure. The equation for angle of departure is equivalent to 180 plus phi, where phi is equivalent to angle made by that imaginary pole with the zeros on the real axis minus angle made by that imaginary pole on the poles on the real axis. So, now similar to that, the angle of arrival at an open loop 0, if you are having any imaginary open loop 0, so here the angle of arrival will be there. The angle of arrival is equivalent to 180 minus phi, again phi is equivalent to the angle made by that open loop 0 with the zeros on the real axis minus angle made by that open loop 0 to the poles on the real axis. So, finally, we are having intersection point of the root locus on imaginary axis. Intersection point of root locus or asymptotes on the real axis is nothing but centroid. Intersection point of the root locus on the imaginary axis is nothing but intersection point. This can be determined by the Routh-Hedge criterion again. So, by solving one problem, you are going to clear so many problems related to this constructions rule. So, in next step, we will see the problem related to root locus technique.